Hello everyone, my name is Rudra Vengurlekar, roll number 2110181. Today I am going to present this critical review of journal paper titled Fluid Flow and Convective Heat Transfer to Fluids at Supercritical Pressure as a part of convective heat transfer course. This paper was authored by J.D. Jackson and it was published in journal Nuclear Engineering and Design. This paper reviews different studies on fluid flow and convective heat transfer at supercritical pressure. This paper provides a comprehensive overview of different experimental and theoretical research work carried out in this field. This paper also provides a brief historical background of how different empirical correlations were developed, historical milestones, and at the end, it also discusses the practical application of this field of fluids at supercritical pressures. So, what is supercritical temperature or supercritical stage? So, upon supplying of heat to a liquid, we can see a transition from liquid to vapor. And if the temperature is less than the critical point temperature, we can see a discontinuity in pressure as we provide heat to the system. So, there is a transition from liquid to vapor where in between there is this liquid vapor mixture state. But if the temperature is greater than the critical temperature, if we are above this critical point, then there is no discontinuity in the pressure, but instead there is a smooth transition as we transition from liquid to vapor. So such a phase is known as supercritical phase. So and the temperature above which this happens is the critical temperature and the critical pressure. So there's something interesting happens in this region, like with temperature. If we plot the variation of different properties at a given pressure, we can see something interesting. Like as the temperature increases, we can see a significant change in different properties such as the thermal conductivity, viscosity, heat transfer coefficient, specific volume, and the specific heat capacities. So we can observe a peak in the specific heat capacity and significant transition in the values of different properties across this temperature. So this temperature is known as pseudo critical temperature, and this temperature is going to be important as we further discuss this paper. So now we know what a supercritical state is, but why are we studying this supercritical state? So to increase the efficiency of power plant, uh, different equipments can be operated at supercritical pressures. Uh, Water acts as a coolant in nuclear reactor, is in the supercritical state. The fuel and oxidizer used in rocket propulsion system, that is S2 and O2 usually, are at high temperatures and pressures, so they are in the supercritical state. So it is important to understand the behavior of fluid in this state. Moreover, helium can be used at supercritical pressure to cool large electromagnets. So there are different applications of this supercritical fluids, but the understanding behind the supercritical fluid, how they behave, is not very clear, and the empirical correlations which we had previously were inadequate to explain the behavior of fluid under different circumstances. So it is important to understand and appreciate the behavior of supercritical fluids. So this is how a system experimental setup of supercritical fluid looks like. So there are two walls. One wall can be heated, other wall can be cooled, and there is a gap between these two walls through which a fluid at supercritical or subcritical state can flow through. And as the fluid flows, it absorbs heat from the heated wall and removes heat and dumps heat to the cooled wall. And as a result, as it moves, we get a fully developed region where the heat absorbed and heat removed are equal. The velocity profile does not change and all. So we observe the different properties in this fully developed region as a function of distance from the inlet length, how the radially properties are varying. So there are different experimental parameters in this setup. So first of all, what fluid which we are using there? Is it CO2? Is it water or any other fluid? What is the distance between these two walls? If it is a pipe instead of two walls, then what is the diameter of that pipe? How much flow rate we are passing through this pipe or gap? What is the wall temperature? what is the inlet temperature, what pressure we are operating this fluid at. Also, the orientation of this setup also plays an important role, whether it is kept horizontally or it is vertically. If it is vertical, then the flow is upward or it is downward. So all these things will decide a different forces acting on the fluid, how the contribution of buoyancy force, the contribution of viscous drag, gravity, and multiple other things. So there are multiple experimental parameters which can be tweaked to and observe different fluid flow behaviors here. Here we can see the variations in temperature, bulk temperature or the wall temperature in two cases. One is upward flowing flow and one is the downward flowing flow. The dashed line is showing the downward flowing flow and the solid lines are showing the upward moving flow. So we can first clearly see the variations in temperature, whether the bulk temperature or the temperature near the wall is higher in case of upward moving flow compared to the downward moving flow. The downward moving flow steadily increases the temperature along the fluid flow path. But in case of upward moving flow, we can see this peak and sharp decline, then again a peak, uh, and again a slight decline in the temperature profile in the wall temperature, and whereas the bulk temperatures are increasing steadily. So why it is happening? Why there is this peak in temperature here, uh, like near the inlet, and then a sharp decline. So uh, this is with different inlet temperatures. And the second plot here, the figure 5, is with is like similar temperature versus distance plot for different heat fluxes. So when the heat flux was high, the temperature near the wall was decreasing and then it increased. Um, and like different kind of profile can be observed for different heat fluxes provided. So why it is happening? So the main reason which this paper tries to address is because of the buoyancy forces acting on it. So we'll see how buoyancy force affect all these temperature profiles. So these are again two plots of temperature versus distance, and here we are trying to observe how the temperature varies for different conditions. So the first plot, the figure 6, is showing how the wall temperature is moving for upflow. So similar to the previous plot, there is one. So here there are two peaks and one sharp decline in between these two peaks. If in the case of upward moving flow, but in case of downward moving flow, there is a steady increase in the temperature, no significant peak or sharp decline. Um, and in both the cases, upward and downward wind flow, the bulk temperature steadily increases. So why there are much variations in this wall temperature compared to the bulk temperature? Similarly, here we the authors reduced the mass flow rate significantly, and for high heat flux, they observed the wall temperatures and the bulk temperature. So they observed similar profile. There are two peaks in the wall temperature, one sharp decline in between, and there is steady increase in the bulk temperature. So through different fluids and geometries, they observed similar pattern in these temperature variations along the length of a fluid flow. For low mass flow rates of fluid flow, they also observed how these peaks, the two peaks which we observed in the last plot, were varying with the in terms of the position in the feeder section. So for different inlet conditions, the peaks were shifting differently. So for higher temperature as the inlet condition, the peak was close to the inlet, and for the lower temperature, the peak was like away from the inlet section, and the bulk temperatures were like more or less steady. But these peaks were just observed in the near the wall temperatures. Whereas in the figure 9, in case of very high mass flow rates, they observed there are no peaks. Instead, the bulk temperature increases steadily, and there is sharp increase in the wall temperature initially, and it remains more or less constant for both the cases, like for upward moving flow and downward moving flow. So that it is quite different compared to the like low mass flow rate of fluid and different initial conditions of temperature. So in terms of theory, how we can understand the behavior of supercritical fluids. So different papers, different researchers tried to explain this differently, but more or less they are attributing these effects to the buoyancy effects and the mixing effect in the supercritical fluids. So they defined this parameter known as thermal loading parameter, which is defined as QWD by K naught T. So QW is the flux, D is the diameter, K naught is the thermal conductivity, and T is the temperature. And there is another factor, the compressibility group parameter. So these two are dimensionless parameter, where beta is representing the compressibility and U is the velocity, Cp is the specific capacity of the fluid. And the Grashoff's number, which is a ratio of buoyancy to the inertial forces, is also modified to some extent in this specific supercritical region. So these dimensionless parameter, we can so there are different limits on these dimensionless parameter to divide the fluid flow in different regions where where the fluid flow can be explained differently. The researchers also tried with Nusselt's number. So the Nusselt number, while considering the buoyancy forces is represented using Nusselt number B, it has a general format of this kind. So there is some constant Reynolds number, Prandtl number, density ratio, and heat capacity ratios. So and there are some parameters like this m and n2, and these equations are fitted to the experimental data, and for different data, different fluids they observe this c values to be different and this n2 values to be different, and the final expressions which we get for the supercritical phase, it is also different from the normal Nusselt's number equation which we which is used in forced convection. So the parameter values are significantly different from the forced convection Nusselt number equation. And this ratio of Nusselt number, while considering the buoyancy force and while considering without the buoyancy force, which is the case uh, in the upwards and downwards wave flow, can be expressed using this equation. So finally, with these empirical correlations were verified for the fluid flow. So first one is for upward moving flow, and the number of peaks, the top of peak, downstreams of peak, uh, for different Nusselt number to the Nusselt number without a buoyancy force, the data is plotted, and the ratio of Grashoff's number to Reynolds number to the power 2.7. So they got these correlation by fitting the data here, and the behavior of upward moving flow is significantly different from the behavior of downward moving flow, and the expression which they got after fitting is also different for this. So this paper was a review paper, and it has done its job very well. It provided a good background information and the various applications where the fluid flow in supercritical state can be very much useful. The paper provided a comprehensive overview of key milestones in history, like development of various empirical correlation, development of the experimental setup, and different experimental parameters. So it also provided the information about experimental as well as theoretical framework uh, developed, and it provided them side by side for better understanding for the reader. But there are still some key areas of improvement. The paper briefly discusses the development of CFD using DNS and LES methods, but it could have been elaborated more for a completeness of this paper. This paper, there are multiple sections which were addressing same issues. These sections could have been combined um, in terms of the theory which they were using for better and readability uh, for a reader. And there I found few typographical errors in this paper. So overall, this was a nice paper, and I enjoyed reading it, reviewing it. Thank you.